So this is, if you recall from frictional faulting theory, which remember frictional faulting theory is sort of this idea that the Earth is kind of in this critically stressed state, right? Such that because there's many arbitrarily oriented fractures in the Earth, and the Earth is constantly under compression from tectonic stresses, then some of those faults are critically stretched, and that sort of puts a bound in different faulting regimes on the ratio of stresses, right? And so if you remember, in a normal faulting regime, what that worked out to was, or what the ratio is, was that guy, right? So if we assume that during depletion that the vertical stress is going to remain more or less constant, then the pore pressure and the horizontal stress, or in this case SH min, are going to change by delta P and delta SH min. Then we can just simply plug in those relationships. Wherever you see SH min, we're going to say SH min minus delta SH min. And wherever you see pore pressure, you're going to have pore pressure minus the change in pore pressure. Right? If you plug that in, and then you just work through some simplifications, it leads to, ultimately, you can solve for that, what Zoback calls the stress path. The change in SH min over the change in pore pressure is equal to this thing. So it's, if you just simplify that equation on top, it leads to this. Okay, and so then if you plug in a value of 0.6, remember when we were talking about friction, it's always 0.6, right? Not really, but it's sort of what we always use. So we plug in a value of 0.6, then this whole thing simplifies down to 0.67. So this is sort of the critical value of the stress path, such that given a Poisson ratio and BO coefficient, if it's above this value, then you're going to promote normal faulting, because these equations came from the assumption of normal faulting. So if you're above that value, then you're going to promote normal faulting. Okay. And so